Hello and welcome to this second presentation related to friction. We're now going to build on the previous presentation related to our simple friction model, which is shown below for recap, where we considered a pair of friction surfaces located on a horizontal plane. In this presentation we're going to apply this simple friction module, but now on an inclined plane. So below is shown this elementary model that is used to analyse the effects of friction. We have a body, an object, a component, etc. of mass, lowercase m. We have an applied force to the body, labelled as P here. And as we know from our previous lecture, friction force always opposes relative motion. So if the applied force to the body is from right to left, then the frictional force is shown from left to right. In a gravitational field, the body will have a weight force, W, which is equal to the mass multiplied by gravitational acceleration, which we always assume to be 9.81 meters per second squared. And to complete a little frictional model, we have a reaction force, or a normal force as it's termed, and that's a reaction from the surface on the body. In most of the problems we considered in our previous presentation related to friction on the horizontal plane, the normal force was equal and opposite to the weight force. There are exceptions to this, but generally speaking that was the assumption we made in most of the questions. However, when we consider the inclined plane, the normal force is no longer equal to the weight force. We'll review that in a few moments. So essentially what you have there is our simple frictional model from our previous presentation. And just to recap, friction force between surfaces. When one body is sliding over another, the tangential force, we denote as capital F suffix F, resisting the motion, is directly proportional to the normal force, capital N, between the contact surfaces. And it's given by the following formula. So the frictional force, FF, is equal to mu, it's a Greek symbol here, friction coefficient, multiplied by the normal force, capital M. And recalling from our previous presentation, there are two types of friction coefficient. There's the static coefficient of friction. This relates to surfaces that are just about to slide over each other. And there's the dynamic, or sometimes termed the kinetic coefficient of friction, and that relates to bodies that are actually in motion. As we've reviewed previously, the static coefficient of frictions are usually higher than the kinetic coefficient of frictions for any given pair of frictional surfaces. So just two slides recapping what we reviewed in the previous presentation. We'll be using this knowledge to underpin our work related to friction on an inclined plane. Let's consider impending motion up an inclined plane. So what we're considering here is a body on the inclined plane, and it's just about to move up the incline. It's not moving up the incline, but it's about to move up the incline. So for impending uniform motion up the plane produced by force P, that's applied parallel to the plane, shown here, we can draw a free body diagram of all the forces acting on the body. Notice the angle alpha here is denoted as the angle of the incline from the horizontal. So considering force P applied parallel to the incline here, it's trying to pull the block up the incline. We know that the friction force opposes the relative motion, so the friction force goes down the incline. Now we know that weight force W always acts vertically downwards, so I've drawn it here. And we know from our frictional model we have normal force N, normal to the incline. And note for reference that the normal force can also be described as being perpendicular to the incline or at right angles to the incline. And notice how we have resolved the weight force into a force parallel to the incline and normal to the incline. So the force parallel to the incline, moving down the incline, is stated as W sine of alpha. That's from basic trigonometry here. And we have a force normal to the incline shown here, and that's W cos of alpha. And again, that's just from using basic trig applied to a right angled triangle, where the W sine alpha is the opposite side and the W cos alpha is the adjacent side of a right angled triangle. W is the hypotenuse, of course. So when considering friction on an inclined plane, what we have to do is resolve forces normal to the incline and resolve forces parallel to the incline. So step 1, let's consider resolving forces normal to the incline. Now, as we know, forces are vector properties, so the direction is very important. So we need a sign convention, and I will state that all positive forces are in this sense normal to the incline. So for static equilibrium, in other words, the block is not actually moving on the incline, it's about to move upwards. In other words, its impending motion is upwards. So resolving forces in the normal sense, that is perpendicular to the incline, we will have N, and that's a positive force because that's in the direction of the arrow here, so positive N. And the only other force we have that is perpendicular to the incline or normal to the incline is W cos alpha, shown in this sense here. And that's negative direction. So in our equation, it will be N minus W cos alpha, and that's equal to 0 for static equilibrium. All we're doing here is actually summating all the forces and equating them to 0. It's Newton's first law we're applying here. If we rearrange the equation for the normal force N, then N is simply W cos of alpha. Now step 2, we're going to resolve forces parallel to the incline. And again, I'm showing a sign convention. Forces up the incline in this case are positive. So for static equilibrium, this time considering the forces parallel to the incline, I have force P shown here up the incline, that's positive to my sign convention. I have the friction force, which will be negative because of its direction down the incline, so I'm minusing the frictional force. And also notice I have this force here, the W sine of angle alpha, down the incline, so I've also got to minus W sine of alpha in my equation. That equals to 0 again for equilibrium. Rearranging for force P, P is equal to the friction force added to the W sine alpha. And of course, remember that frictional force is actually mu n. So we could replace this frictional force here with the mu n. If we now consider impending motion down the inclined plane, so again, it's a free body diagram. Notice here the frictional force, though, is now up the incline because the impending motion is down the incline. Friction always opposes the relative motions. If we resolve forces normal to the incline for impending motion down the incline, it will be exactly the same equation as for impending motion up the incline, derived on the previous slide. But if we resolve forces parallel to the incline, we will generate a slightly different equation because the frictional force is in a different direction. So again, as previously, I have a sign convention saying forces up the incline are positive. So for static equilibrium, our equation is P, positive up the incline, and that's added to this time the frictional force, which is also in the positive sense because the impending motion is downwards here, so we add friction force to the equation. But we still have here the component of the weight force, W sine alpha, acting down the incline. So it's minus W sine alpha in our equation. And again, that equals to 0 for equilibrium. Rearranging for force P, this time it becomes W sine alpha minus the friction force. If we compare that back to the impending motion up the incline, we had P is equal to the friction force plus W sine alpha. So there's a change of sign on the frictional force here. Just note for reference, if the value of force P calculates to be negative, then its direction is reversed. In other words, the block needs to be pushed and down the incline. And that can happen if we have very, very high frictional forces. Let's consider an example of a body on an inclined plane. In this particular example, the applied force P is parallel to the plane, shown here. You'll see in some questions the force P is actually applied horizontally, but in the questions we're going to consider in this presentation, our forces are applied parallel to the incline. So our scenario is a block having a mass of 102 kilograms is stationary on a plane that's inclined at 25 degrees from the horizontal. We're assuming that the friction coefficient is 0.35 and we have to find the minimum force P required for the following scenarios. Scenario A, to pull the block up the slope, up the incline, and scenario B, to keep the block stationary on the slope, on the incline here. What we're going to do is resolve forces as shown on the previous slide, first of all normal to the incline and then parallel to the incline, from where we can attempt to solve these two scenarios. If you want to have an attempt at this question, I would encourage you to stop the presentation and do so now, but I'm going to work through the full solutions on the following slides. So example 1, here's our solution. First thing to do is to extract the information from the question. And I'm going to calculate the weight force W because I will need it in my calculations. We're given in the question the mass of the block, 102 kilograms. We multiply that by 9.81 meters per second squared, that's gravitational acceleration. We can find the weight force, which is approximately 1,000 newtons. We also know from the question that the incline plane is at 25 degrees to the horizontal, so my alpha is 25 degrees. And the friction coefficient is stated as 0.35, so my mu is 0.35. On the right hand side I've drawn my free body diagram for impending motion up the incline, because that's the first scenario. We've got to find the pull on the block up the slope. So for part A, the impending motion is up the incline, so resolving forces normal to the plane first of all, again using my sign convention. So adding up all the forces, they must equal to 0. Newton's first law here. So we have our normal force, that's positive. And we subtract the component of the weight force shown acting in this direction, the W cos alpha. So we're minusing that in the equation, W cos alpha. That equals to 0. There are no other forces normal to the incline to consider. So we can clearly see that the normal force is equal to W cos alpha. So inserting the values, normal force is W, 1,000, multiplied by the cos of alpha, the cos of 25 degrees. That evaluates to 906 newtons. So that's a normal force in this particular case. So note again, as the block is on the inclined plane, the normal force does not equal to the weight force. It's equal to a component of the weight force, the W cos alpha. Example 1 continued. Part A here, motion up the incline. I just repeated this calculation from the previous slide for convenience. So now let's resolve forces parallel to the inclined plane. Again, I'm showing my positive notation for the forces, equating to 0 for static equilibrium. P is positive, so up the incline, minus the friction force, shown here, it's down the incline, and then minus a component of the weight force of W sine alpha, shown here, and that's equal to 0. Rearranging to find force P, P is equal to the friction force plus the W sine alpha. But we know that friction force is equal to mu n, so I can actually replace the friction force here with mu n. Now we're going to substitute in the values from the question and also the normal force shown above here into the equation. We have P is equal to the coefficient of friction, which is 0.35, multiplied by the normal force shown above, 906 newtons, and then we add to that the W sine alpha, so that's 1000 newtons for the weight force, and then sine of 25 degrees. Evaluating, we find that P is approximately 740 newtons, and when that force is applied, the body is on the point of moving up the incline. Any increase in force will start to move the body up the incline. Here's example 1 continued. This is part B here. We're considering impending motion down the incline plane. If we resolve forces normal to the incline, it's exactly the same calculation as shown previously. We just have normal force equal to this component here of the weight force. So the normal force value is 906 newtons as calculated previously. But resolving forces parallel to the incline plane, again with my sign convention shown here, this time we have the friction force in a positive sense, it's up the incline, added to the applied force P, positive sense, but we still minus the W sine alpha force, in other words this component of the weight force, because that still acts down the incline. That's all equal to 0. Rearranging, force P is equal to W sine alpha minus the friction force. Again, the friction force is equal to mu n, so we can replace this friction force with mu n. And again, substituting the values, noting that n is equal to 906 newtons from the calculation on the previous slide. We can determine the value of P, and that's approximately 106 newtons. So, if we apply a P of 106 newtons, the body is just about to slide down the incline. Any reduction in force P and the body will move down the incline. So that's an example of friction on an inclined plane, part A, where we're considering impending motion up the incline, and part B, when we're considering impending motion down the incline. Notice a very similar approach in both cases. The only thing that's different is the direction of the frictional force, depending on if the bodies tend to move up or tend to move down the incline. Here are some tutorial questions, all related to an applied force P that's parallel to the incline. There are 3 questions shown, 1A through to 3A, all requiring solutions very similar to that shown in the previous example. The answers are shown in the brackets on the right hand side of each question. I'd encourage you to stop the presentation and attempt these questions now. I will show the full solutions to question 1A on the following slides. So question 1A, here's the full solution. So a block of mass, 1350 kilograms, lies on a gradient that's inclined at 60 degrees to the horizontal. Given the kinetic coefficient of friction, mu k is 0.4, and the static coefficient of friction, mu s, is 0.5, we're asked to determine the following. 1. The pulling force required parallel to the incline to hold the mass up the gradient at uniform speed, and 2. The pulling force parallel to the incline required to prevent the load from sliding down. Let's extract information from the question. We know mass of the block, m, is 1,350 kilograms. From this we can work out the weight of the block, w. Weight is mass times gravitation acceleration, so multiplying the mass by 9.81 meters per second squared, we have a weight force of 13,243 newtons. The angle of the incline, alpha, is 60 degrees to the horizontal. I'm also given the kinetic coefficient of friction, the mu k, is 0.4. We use that in part 1 of the question. And the static coefficient of friction, the mu s, is 0.5. We'll use that in part 2 of the question. So question 1 continued here. So part 1, we're trying to determine the pulling force P required to hold the mass up the incline. So we're trying to find this force shown here. So step 1, resolving forces normal or perpendicular to the incline, equal to 0 for equilibrium. Using my sign convention here, positive n minus the W cos alpha, W cos 60 degrees shown here. And these are the only two forces that are perpendicular to or normal to the inclined plane. Rearranging for n, normal force, that's W cos alpha. Inserting the numbers, we know W, the weight, the angle alpha, 60 degrees. We can evaluate the normal force, it's 6,622 newtons in this case. Step 2 here, resolving forces parallel to the incline. Again, forces parallel must equal 0 for equilibrium. So my positive direction is in the sense of P here, so it's positive P minus the friction force, it goes in the opposite direction, and then minus the component of the weight force, the W sine 60 degrees shown there, minus W sine alpha is equal to 0. Rearranging for P is equal to W sine alpha plus the mu n. Again, notice that the friction force here has been replaced with mu n here. So calculating P, and notice we're using here 0.4. That's the dynamic or kinematic coefficient of friction. That's because part 1 of the question wants us to hold the mass up the incline at constant speed or uniform speed. So that evaluates to 14,180 newtons. That would be the force required to move the block up the incline at uniform speed. In other words, it's not accelerating. Question 1 continued. This is part 2 now. We've got to find the pulling force P required to keep the mass at rest on the incline, to stop it sliding down the incline. In part 1, if we resolve the forces normal to the incline, we'll get exactly the same answer as we did in part 1. So the normal force will evaluate to 6,622 newtons. But in step 2 here, resolving forces parallel to the incline, this time we'll find that the friction force is in the opposite sense because the impending motion is effectively down the incline here. So we'll have positive P, the pulling force. We'll have positive friction force because it's acting the same direction as the pulling force. And then we'll have the minus W sine alpha, this component here of the weight force. Rearranging the equation and inserting the mu n for the friction force again, we can calculate the value of P. Notice this time we've used the static coefficient of friction because part 2 wants us to ensure that the mass is at rest. So that would be a static coefficient of friction, it's not moving. Inserting the values and evaluating, force P now is 8,158 newtons. So that's the force required to keep the mass stationary on the incline. I'm going to take you through another example, example 2 here. The sketch shows a vehicle of mass 0.75 ton driving up a rough incline of angle alpha 6 degrees, angle alpha shown here. The vehicle's engine produces a driving force, labelled P, that's parallel to the incline of 2.65 kilonewtons. 3 parts in the example here. Part A, we're asked to sketch the free body diagram of all the forces acting on the vehicle. Part B, if the coefficient of friction between the vehicle's tyres and the road surface is assumed to be 0.14, we've got to determine the maximum friction force that's exerted on the vehicle. And finally, part C, we've got to determine the acceleration of the car up the incline. stating the answer to 1 decimal place. So on the previous examples in questions, we were essentially applying Newton's first law, normal to and parallel to the incline, because our objects were either stationary or they were moving at constant velocity. But in this particular question, in part C, we're asked to determine the acceleration, so that will be applying Newton's second law, parallel to the incline. If you want to attempt this question without further assistance, I would encourage you to do so. The answers are shown in the brackets here. You need to draw the free body diagram first of all, and calculate the friction force, then finally calculate the acceleration. I will show you the full solutions on the following slides. Example 2, here's a solution. First of all, let's extract the information from the question. So the question states the mass of the vehicle is 0.75 tons. We need to convert that straight away into kilograms. So 0.75 ton is equivalent to 750 kilograms. Knowing the mass, we can now calculate the weight of the vehicle. So weight is mass times gravitational acceleration. 750 kilograms multiplied by 9.81 meters per second squared. That's a weight force of 7,357.5 newtons. We're given in the question the driving force P, that's parallel to the incline, is 2.65 kilonewtons. So driving force P here, 2,650 newtons. The angle of the incline is 6 degrees to the horizontal, and the coefficient of friction given in the question is 0.14. So solution continued. This is part A. So draw the free body diagram. Here's the free body diagram on the right hand side. Notice I've just used a rectangular section for the free body. The car is just considered a rigid body, so a rectangular section shown is acceptable. And don't forget, a free body shows all the forces acting on the body. So in this case we have driving force P, shown here up the incline. The frictional force is opposing the driving force, so it's down the incline. And in the vertical sense, I have my weight force acting vertically down, but that can resolve parallel to and perpendicular to the incline. So resolving the weight force perpendicular to the incline, we have W cos of alpha. So the normal reaction force N is equal and opposite to W cos alpha. And I also have my component of the weight force resolved parallel to the incline, shown here, and that's W sine of alpha. So there's my free body diagram for part A of example 2. Example 2, solution continued. Here is part B. We're asked to find the friction force. We know that friction force is equal to mu times N. We know that N is equal to W cos alpha from our previous balance. So W, we calculate on the previous slide, 7,357.5 newtons. That's multiplied by cos of the angle alpha, cos of 6 degrees in this case. So our normal force evaluates to 7,317.2 newtons. So now we've got the normal force in our equation. The friction coefficient is given in the question. So we can evaluate the friction force parallel to the incline. That's 1,024.4 newtons. So that's this force here on our free body diagram. Example 2, solution continued. This is part C. Again, we're going to resolve forces parallel to the incline, but this time we're going to apply Newton's second law. In all the previous work, we applied Newton's first law because the body on the incline we were considering was either at rest or was moving at constant velocity. In this particular question, we're told that the body is accelerating up the incline, so that's a Newton's second law problem. So instead of summating all the forces to equal to 0 for Newton's first law, the second law says summate all the forces and they equal to mass times acceleration. We reviewed Newton's laws of motion in a separate presentation. So resolving forces parallel to the incline, if I say propelling force P is positive up the incline. We have positive P. We have the negative component of the weight force, W sine alpha, so minus W sine alpha. Friction force, as always, opposes relative motion, so the friction force is down the incline as the motion is up, so we minus the friction force. That's all the forces applied, parallel to the incline, so we now equate them to mass times acceleration. What I've done on the next line is rearrange to find the acceleration, A, so simply divide both sides of the equation by m. So we end up with A is equal to P minus W sine alpha minus the friction force, all divided by the mass of the vehicle. Inserting the values, the propelling force is given in the question. We've calculated W previously. The angle of the incline is given in the question. And the friction force we calculated in part B. The mass was also given in the question, 750 kilograms. So that evaluates to an acceleration of 1.14 meters per second squared, or 1.1 meters per second squared to 1 decimal place. I will leave you with exercise 2 to attempt at your own pace. Here we have a sketch on the right hand side that shows a car of mass 1,158 kilograms. It's been driven up a rough incline of angle alpha 10 degrees. This is angle alpha here 10 degrees. If a constant frictional force is experienced by the car during the motion, we've got to determine the driving force P. So this is force P parallel to the incline, which the engine must supply to accelerate the car at 2 meters per second squared. We can assume that the coefficient of friction between the car tyres and the inclined surface is 0.2. So I would encourage you to stop the presentation and attempt this question. The answer is shown in the bracket. I would encourage you first of all to draw the free body diagram of the car on the incline. I would then suggest you work out the frictional force, given the information in the question, and then apply Newton's second law parallel to the incline to work out the engine driving force P. Here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.